So good afternoon, my name is Raffaello Secondo. I'm a PhD student actually with the University of Montpellier, but my work is based at CERN. And today I'm going to speak on behalf of the CERN Radiation to Electronics group, which is the group that takes care of all the radiation testing and the testing of equipment at CERN that is performed for installation inside the harsh areas. And the title of the talk is Components and System Testing at the CHARM Mixed Field Facility. Just to give you a brief outline, I'm going to talk a little bit of the CERN radiation environment, and then we'll go through explaining a bit the radiation testing effort that we have at CERN. And then we'll go through the details presenting the CHARM facility. It's a new facility that ended commission at the end of 2014, and right now, last year, basically in 2015, we had the first tests. We had the first run in, let's say, a more operative configuration of the facility. And I will give a bit of details on the layout, on the structure of the facility, on the irradiation area, and on the environments that are represented inside the irradiation area. Then I will give you just a few examples of the tests that we did in 2015, and I will just go through the conclusions at the end. So CERN, I don't think, needs a lot of introduction. You all know it's a European organization, which is based in Geneva. The flagship experiment is the LHC, which is based half in France and half in Switzerland. Actually, physically, it's more in France than Switzerland. And of course, we deal with really strong radiation fields that are generated through different collisions of protons and protons, of course, in the interaction points of the accelerators. In the experiments, namely, the two most important are ATLAS and CMS. But of course, we have very strong radiation fields pretty much over the whole complex. We have stronger fields in the, for instance, in the interactions between the protons and the collimators, which are the most hot zones inside the LHC, and of course we have beam gas interactions. And in terms of radiation effects on components and systems, of course we deal with TID effects, with displacement damages, and of course a lot with single events. In terms of the environment, for instance, of the LHC tunnel, we are pretty much dominated at high energies by protons and pions and kaons, so by hadrons. And at lower energies, we have a strong contribution of thermal neutrons. In particular, we have a lot of interaction between the thermal neutrons and components that have boron materials inside, which is the case, for instance, of components that were installed in the old times, like 20 years ago or 15 years ago. There is a strong effort in terms of modeling for simulation and simulations of the radiation environments. We extensively use the Monte Carlo code FLUCA, which I'm not going to talk about it right now, but it's extensively used. And of course we use it for predictions of the irradiations in the areas. So testing at CERN, of course, we have several applications, several systems that are installed in the whole complex. For instance, we have systems of cryogenics, power converters, vacuum, and any kind of applications actually. And we extensively use COTS components because they are cheap, because they have very good electrical performances in their lifespan, at least, and because they are extremely available, because we need to replicate it several times inside the systems in the design. So we have a strong radiation testing effort right now. And the facilities that we use the most for proton tests with a focused beam, we do test the PSI, namely in the PIF irradiation area, here, just a picture reporting, which is close to Zurich in PSI. And we recently have also a cobalt-60 facilities for TID effects that is based at CERN. But of course we have strong requirements. We have, for instance, certain systems can tolerate only up to 10 failures per year. That leads to an LHC beam dump. So every beam dump for us is a huge problem. Just to give you a few numbers, the fluence of high energy hadrons is like 10 to the 9 square centimeters per year. If you compare it, for instance, with the ISS orbit, this is like 1 order of magnitude less or even like 10 to the 5 instead of 10 to the 9 in case of ground applications. So we deal with really high fluences. And this translates for a single component into 14 hours of beam time at PSI, for instance. And it's not just that. We also have different components and different batches that are involved that we need to test, because the date code also is important. And in order to do this, in order to be efficient in terms of resources and in terms of time, we needed a more efficient approach for system and component tests. So this is why we designed this CHARM facility. CHARM stands for CERN High Energy Accelerator Mixed Field Facility. There were also other names that were candidates, like CHER, for instance, CERN High Energy Research Facility. But CHER in French means expensive, so we decided CHARM was a bit better. And the main purpose is basically, of course, to test several components at once. For instance, if we take a PCBs right now that we use for PSI tests, with a focused beam you can test a few components inside the diameter of the proton beam. But inside CHARM, instead, the approach is to test in a specific test location where we simulated and measured the particle spectra at that location, where we know the dose rates, where we know the flux rates, and then from that we can extrapolate the cross sections of the components and evaluate the degradation over TID and so on. And also to test larger systems at once by placing them in a particular specific location where we know the representative environment of that location. And of course we can have different environments, for instance the accelerator ones, the space one, the ground and avionic environment. And of course we can also always expose the components directly in the beam for really high flux tests. And in this case, basically, like this, we can test the tunnel and the shielded areas of the ADC, for instance, but also we can test nanosatellites or other systems. So this is just a 3D view of the facility from the top. The access is from this corridor, then you go through this corner, and here there is a patch panel area, which is the patch panel is where we plug the cables that are going through, that are going into the irradiation zone, and then that are successively plugged to the equipment. This is the target and test zone. Here you can, I don't know if you can see it very well from this corner. The beam lines this, basically goes through here and then crosses the facility, and this is the beam dump. And here is the storage area where basically we prepare the tests before installation inside the target zone. This is the picture of the facility taken from one of the corners of the irradiation area. The test locations are placed here and here in this basically L-shaped corridor. This cage here is allowing some shielding, different shieldings to come in and to be moved inside and outside of the facility in order to achieve different configurations of the facility. The proton beam comes from a hole placed right here and hits this point here, and then the beam dump is just behind. The proton beam is the 24 GeV proton beam coming from the extraction of the proton synchrotron. So we have the proton synchrotron delivering us the particles, and of course this means that we are tied to the schedules of the proton synchrotron. So we are delivered the beam, but of course if there is any problem with the booster, with the Linux that are ahead of us, of course the facility needs to stop and needs to wait for the operators to deliver the beam again. Then there is a target that is placed in position more or less right here. We have three types of targets: copper, aluminum, and aluminum with holes. The patch panel is looks like that, and it's just placed here on the left in this corner. And how we place the equipment inside, basically we have these chain holders that wrap up all the cables and that are connected to the equipment racks that are placed inside using a mount truck robot, basically, that is commanded, is controlled from outside and places the equipment in position. For instance, this one is taken in the corner where this picture was shot. So the irradiation area looks like that from a schematic point of view. The beam comes through here and shieldings are basically moved in this part. We have the lateral positions that are this 1 to 8. 1 to 8 basically. And then the longitudinal positions are here. And of course we have the in-beam position over there. So this position here have lower fluxes compared to the longitudinal ones that are closer to the beam. In this way, for instance, we can have different spectra reproduced. Myself, for instance, I tested namely in position 4 because it's the one that represents at least 3, 4, and 5, at least the ones that represents better the LEO orbit environment, since I deal specifically with nanosatellites. But for instance, for equipment into the accelerator and the shielded areas of the LHC, it's more like around this point, which is closer to the beam. And of course, our approach is based on the energy deposition and over a sensitive volume, which is first simulated using Fluka calculations with the Monte Carlo codes. For instance, here you can see the high energy hadron flux as it is expected for a particular configuration. And in this one, for instance, you can see the locations 10 to 13, which are the ones here, in the longitudinal positions, are roughly 10 to the 10 square centimeters per hour, which is more or less 1 year in the LHC tunnel. So it's a very high fluxes. Instead, for instance, the ones here are the ones more for ground application and for the LEO orbit, for instance, that namely for the space environments. But of course, we don't just rely on simulations. We also measure the dose and the high energy hadron fluence at every test. How we do it? We do it using the Raman system. It's a radiation monitoring system. It looks like this, basically. It's a small box, mainly made of, actually all based on COTS components. And it measures the dose with a couple of RADFETs, the high energy hadron fluence with strong memories, and also the displacement damage with the silicon pin diode. And we also can connect it to a deported model with RADFETs and pin diodes also here to reach farther areas and to basically avoid killing the main boards that are on the Raman system. So we deploy it by attaching it to the equipment. For instance, you can see some pictures here inside the radiation area. And every time we cross-check the fields and we improve the calibration at every radiation run, no? In order to deliver to the user not just a prediction of the spectra, but also a real measurement over the sensitive volume of the equipment. But why is it important for us to reproduce the high energy hadron spectra? It is really, really important because basically we are dominating, in terms of single events, we are dominated by hadrons, by protons and neutrons, for instance, inside the facility. And we did some tests that showed that, for instance, for materials that have for high-end materials, high atomic numbers, for instance, that materials like tungsten that are plugged inside the devices, we had a strong impact on the single event effects depending on the energy. So if we did fit of the models that we have based on data taken, for instance, at 60 MeV or at 230 MeVs, the cross-section that we extrapolated were saturated at a completely different point. So we had, for instance, we can achieve a factor of difference of 100, for instance. So it's important that we reproduce the whole broad energy spectrum from thermal neutrons, from millielectron volts up to 1 GeV, for instance, or even more, in order to have a cross-section taken over a broad range of energies. And just to give you, just to show you a comparison of the radiation environments as simulated between CERN, for instance, and the LHC tunnel, we could see that there is a very well representation up to 50% of the energy of the fluxes. And then the particle spectra are not really well represented around here, which is basically around 10% of the spectrum. But of course, at higher energies, the contribution is smaller, so it's neglectable, let's say, this part. In terms of the ISS orbit, for instance, for the space environment, we have a very well representation up to even more than 50%, much more than 50% of the spectra, and we achieve very good representation around here. And then there is this trail here that is not very well represented at higher energies, This one is basically induced, is due to the galactic cosmic rays that are not well represented inside the facility, but since they are, their contribution is below 1% at least of the spectra, it's again negligible for us. So just to give you a brief view of the tests that we did last year, we tested, for instance, a function generator controller that is scheduled for installation in the LHC for providing applications of power converting namely for the magnets, for dipoles and quadrupoles. And we did tests of current consumption over TID as well as single events. And of course we tested the overall functionality. In this case it's pretty complex equipment because it has multiple daughter boards plugged into a motherboard in a big rack. And actually we can see here a couple of those FGC controllers inside the charm area. Also we performed other tests. For instance, there was a group that deals with cryogenics that tested their electronics equipment that measures temperature and pressure of the liquid helium, for instance. You can see here the radiation monitors that are always attached to the equipment. We tested an array of red and green LEDs, so you can see a matrix here. If I remember correctly, there was a camera that was taking the luminosity of the LEDs and was checking it over the TID data. And we tested also a module for a payload study for one new CubeSat. The project name is CELESTA. And we did several tests like CL detection, measurement of the dose and the high energy flux monitoring. We tested the FPGA functionality, the communication of the board and the power consumption. And of course we keep doing tests on new sensors for our radiation monitoring systems and also on upgrades of the firmware and possibly validate new firmwares, for instance, in order to give again an even better experience to the users in terms of the data collected. So just to summarize, the CERN activities of course require an extensive use of the COTS components, and for this there is a strong testing effort right now. We have several particle spectra reproduced inside the CHARM facility, namely accelerator, space and ground environments are the ones that most used, at least. They are achieved through different configurations of the facility, using different targets for the secondary shower of particles, but also different shieldings inside the facility. And this allows also tests of multiple components, but of bigger systems as well. We had our first operative successful run in 2015, finished commissioning around October, November 2013. We did the first tests in May of 2015 and we ran through December last year. And just in case, of course, there is an interest, how to test a charm, there are a couple of contacts that are the people responsible of the facility. And of course, in order to test a charm, we need to go through a discussion with the charm responsible, and you need to find, it is needed to find a common interest that can start a collaboration agreement with, between CERN and the users. Because so far, of course, the users that tested inside the facility were mostly just inside CERN, so different sections of CERN that tested their equipment for their use inside the LHC area or inside the CERN complex. And then if there is a collaboration agreement that is signed and the collaboration can start, of course it is possible to talk about the aim of the radiation test, the cabling needed, which kind of guidelines are needed for testing, and of course the discussion can be done at CERN or via teleconference. This is to be foreseen since the facility is pretty new. So thanks a lot, this ends my talk.